Are we live? I think I'm live. Nice. I think I'm live. Absolutely. Okay, cool. Let's get the link. Let's get the linkety link. I think I'm live. Oh, it's mute. Oh, I'm hearing myself. Wild. I think we're live. Are there any students in chat? Are any students in chat? Okay, let's do monkey type for 5 minutes. Monkey type for 5 minutes. Then we're gonna press play on VLC, and hope it works. I can't actually talk for 90 minutes, so I like recorded two 45-minute chunks. I think they'll just autoplay into each other, but I have no idea what's going to happen. Are there any students in the chat? That's what we want to know. Are there any students at all? Kind of feels like I'm talking to myself here, and that's okay. Okay. Press here or any key to focus. All right, I need to focus up. Oh, I got 4 minutes until class starts. If these how, what, run to, man, never he not stand against real word, could, if, will, it, interest, now, then, do stand, he, help, you, number, time, okay, 188, okay, how do you retry? What's the retry key? I'll go again. What is that? You do next? I feel like there's no students in chat. Alright, we'll go again. New one. Through increase, which present what little then, so each then get or state at not without part place, seem then only by last small might may their time turn need do feel who because I'm getting worse. I'm getting worse. Okay, gotta put a cricket in Discord. Make sure people know. Hey, there's two watching. Hey, someone else is watching. I wonder if I'm just watching it twice. Okay, alright. New test. Can keep person such large part go she give only here thing public can too good look against that system year for on we however problem into long seem would will home. Okay. Oh no, someone's locked. Better to be locked than unlocked. You can be locked, stocked, and barreled. By the way, with that, I got a YouTube chat notey, and it ruined my accuracy. Look at that. That's why it's harder to stream. Can keep person such large part go she give only here thing public can too good look against that system. Okay. We're gonna retry this one. Can keep person such large part go she give only here thing public can too good look against that system year for on we however problem into long seem would will home to place that's good. That's good. That one's going in the disc. I'm proud of myself there. I hope you're all proud of me. 3 watching now. Wow, 3 watchers. That's so many watchers. Okay. Next test. How many seconds do we have? I have time for one more. Okay, all right. Great, because my hands weren't on the keyboard when I started. Might I and okay, no. Where are my hands? Okay. through, place, a, great, few, leave, need, any, win, another, plan, early, after, new, become, on, both, but, home, look, no, part, more, late, both, order, house, form, good, go, during, think, form, out. Okay, yeah, we take those ones. All right, by my count, it's around 110. Let's go ahead and, I think it's lock in a clock. That's what I've heard. So we're going to go ahead and we're going to close monkey type. It's gone. It's vanished from this world. And we're going to go ahead and get going. So here we go. Bits. Hello, students, and welcome to Systems in Rust. Today is the Bits lecture. This is the 0th day of the 3rd week of CS 271. And today we're going to be talking a bit about information because it's going to become handy coming up. Just a few announcements before we begin. The Wordle assignment is out and it is ongoing. That is due Friday at 2:40 p.m. Pacific time. The next assignment is more of a puzzle assignment. It's not going to take a large amount of time, but it's going to take a certain amount of thinking, and perhaps a form of thinking you haven't done before. That is called macros. That's ready after this class, but will be more properly ready after the lab on Wednesday. So you can work on that whenever you want, but I would invest time in Wordle primarily. Today we're going to go over how information is encoded within a computer. I'm going to talk about bytes. I'm going to talk about bitwise operators, and then we're going to talk a little bit about endianness. There's a sort of latent or hidden learning objective going on today underneath all of these things, which is that the code I'm going to write to demonstrate some of these things is going to use recursion within match statements. This is a style of code I don't write in the other systems programming language. Basically, I don't write in Python either. It's sort of uncommon. It's not idiomatic Rust. I don't think it's necessarily how the Rust designers intended the language to be written, but it is certainly an intended form of supported writing. So I'm going to show that to you today. I suspect you haven't seen much code written that way, and so I thought today was a good time while we were playing around with this to also show you some of the language features that you wouldn't get in another language. And so that'll mostly be happening towards the end as we get closer to ending this. So let's talk about bytes. The way I think about bytes is fairly straightforward. The usefulness of bytes is not necessarily only that it's a physical thing that actually exists, right? It's useful as a term. A byte is an ordered collection of 8 bits, right? And a bit is the atomic unit of digital information. But when do we think about these things? I mean, we never think about these things when we're just using computers to do stuff, right? We almost always are thinking about the information in computers as having some accompanied representation. I think the most common accompanying representation is numbers. Oftentimes we think of it as numerically, but of course there's also graphics, right? An image, we can think of it as being a 2 or 3-dimensional, depending on how you view colors, array of numbers, but we can also view that as just like storing visual information, right? And it's not that different from how my eye parses visual information. We can think about text in the same way, right? I don't think we necessarily think of web browsers as particularly doing numbers, right? They, for the most part, take HTML and then turn it into a visual representation, right? But there's numbers going on under the hood there. But especially the early computers, the first computers, when we were using the term compute, right? When you're trying to compute something, oftentimes you're trying to compute the solution to an equation, right? And so when I think of using computers in that classical sense, I think very much of NumPy and Numba, which is the sort of Python high-performance numerical computing libraries. I think of Julia, which is a relatively young language that you would not write software in Julia, right? But you would probably solve a differential equation in Julia. And then Fortran. One of the very early languages, a very important language, a language that was redone in the 90s and still sees much use in scientific numerical computing. And it just stands for, I believe, formula transcription or transmission or something, right? It was intended as a language to write down mathematical equations, essentially using a typewriter, because those were the keys they had access to at those times. Excuse me. So these languages are very good at numbers. And that is one of the things you do with a computer. But that is not the only thing you do with a computer, and it is not what you are doing with a computer when you are trying to write an operating system. Specifically, when I think of the the important applications for a systems programming language, a language like Rust, or the other systems language, which is C. What these things are really doing is you're not necessarily reaching for them when you want to use a computer to solve a problem. You're reaching for them when you want to configure a computer system so that later when you write Fortran or Julia or NumPy, everything just sort of works, right? This is about building devices. It's about taking electronics and turning them into tools. When we're working with electronics, we're not directly, for the most part, necessarily working with numbers. There's certainly numbers going on there, and those are now suddenly physics numbers instead of mathematics numbers, is maybe an abstraction way to think about it or something, right? But we can, and we're sort of cheating a little bit here to think about these even as zeros or ones. Oftentimes they're thought of as switches that are open or closed, right? When we start thinking of a computer as a collection of switches that can be open and closed, and just someone or some piece of machinery has to take those switches and somehow convert them into a numerical value, that starts to me to feel like processing more than computing, right? And when I think of processing, historically we've said information, we increasingly say data now. And if you get past the zeros and ones, it turns into signal processing. So signal, information, or data processing. This is when I start reaching for lower level languages, not necessarily low level languages, because that's a fraught term, but languages that are lower level than NumPy, Julia, and Fortran. And what are those? Those are the C programming languages, to a lesser degree C++. That is assembly languages, which is for a given piece of hardware, there is some corresponding assembly language. That is a sort of, usually I think like electrical engineers are dealing with that, but computer scientists do as well. And one of the important contributions of a language like C is that it can be used to take programs and turn them into assembly language, right? And then most recently, Rust has been sort of vying to join this pantheon, right? And it is 50 years newer than these other two things. These languages, like famously, like C doesn't have square root in it without like including a library function, right? You don't use this to do your math homework, and by math homework I mean your math homework from middle school, right? You use these things when you want your computer to start working, right? Or you're like, oh, my computer doesn't know what a keyboard is. I should write a piece of code that tells the computer how to interpret a bunch of switches being open or closed at some microscopic level, not nano. But yeah, so we have these tiny switches that correspond to whether a key is touched on my keyboard or something, and somehow I want my computer to know that, like, hey, when I press the VI and then press enter, it needs to open Vim, right? This is highly non-obvious to computers, right? And if I even just move anywhere else on my computer, if I is there a search bar here? Probably. I don't know. Oh, I can do Control F. Like if I type VI over here, like it does something different, right? Differently. And so somehow you have to program all of those things, right? And those things aren't really numbers. They're they're state machines or they're graphs or something, right? And so when you're just trying to get a computer to work at all, that's when you start thinking of it in terms of electronics, and that's when you start thinking of it in terms of bytes. So when I use the term byte, I'm not just referring to an ordered collection of 8 bits, because to me, oftentimes an ordered collection of 8 bits is an unsigned 8-bit integer, or even perhaps a signed 8-bit integer, right? And that's often how NumPy thinks of them, right? When I'm thinking of bytes in terms of information, I'm thinking of it much closer to how we use them in cryptography, or perhaps how you might use them in an operating system to encode, a series of flags, which they're often called, about like what state the processor is in, things of this nature. And this also happens to be a pretty good way to read arbitrary file data. So I think earlier this term I showed us an example of what Firefox looks like if you just open the file as a text file, right? And it's not human readable. It doesn't look like numbers. It doesn't look like text. It's something else. So I think Rust is relatively good at doing this. I have not yet been convinced it's as good at doing this as C is, but I do think it's better at this than any non-C language I've worked with. So when we're talking about the lower level languages, I'm talking about this idea of sort of the hardware-software interface, which is what I talk about, which is like, how do I take those switches and get software to eventually run on this thing. And Rust has the benefit of it tends to not sort of obscure these things. So I think if I come over here, remember how Python works? I think I can just say like open dev random, and I can just like read from that. Oh, is it gonna take everything? That's a bad idea. Okay, I'll do it in a script. So we'll do Python C open dev random read line. So we're just going to read, because dev random is not a well-structured file, this will simply read until it hits a new line, which is, at probability 1 in 255, it's going to hit the new line, right? Let's see. Oh, those need to be inside another kind of quotes. There we go. Has no attribute. Oh, there's no... Right, okay, so here's something obnoxious, right? When I ask Python to just read from a file, it can't. It doesn't know how to decode bytes. How ludicrously annoying is that here? It just can't do it, right? It just, so, and probably I can program Python to deal with this. On the flip side, or no, we'll do head. I'm going to take one. Head takes the first n lines of a file. I specify the n here. By default, it's 10. That's too many, so I'm going to say 1. I'm going to take the first line of dev random. And okay, my shell script can handle this. Why is that? Because this shell script is the operating system. It's written in C, right? Head is a command line utility in the, GNU core utils, or whatever, wherever it's written, right? So someone wrote this in C in 1970, right? And it's still around, and it can just deal with information, right? So Python gives up. We can't handle bytes. The thing written in C is just fine. And this is the same thing we were able to do in Rust, right? So usually, if you're just using a computer to do something, it's not necessarily the case, I think, that you actually want to be thinking about bits and bytes, right? That's the special case that you want to be thinking about dealing with bits and bytes. When you do want to be thinking about bits and bytes, because something like this happens, because you want to use your hardware random number interface, right? So you can actually have truly random information, right? Yeah, I mean, you might be reaching for one of these languages, right? When you want to write performance accelerated code on your GPU, maybe you want to be reaching for one of these lower level languages, and that's less true now than it used to be because there's better Python support. But the newest and most advanced and highest performance technologies are frequently going to require going down to this lower level and thinking about the actual information we have. Excuse me. Okay. I want to just emphasize, and I think this is this class only, and it's probably going to be the combination of me in this class only is going to have this view, but just for the sake of keeping concepts consistent in our minds, I'm going to emphasize that a byte is a hardware idea, or at least a hardware-software interface idea. Perhaps that should more properly say hardware-software interface, because I don't think bytes exist in hardware either. They only exist when hardware is trying to talk to software and trying to communicate something, right? These things do actually physically exist. They correspond to either an electrical charge or the absence of an electrical charge that is present in a transistor. We don't have to think of them that way, right? We can just think of them you can think of them as numbers, right? You can think of them as anything like. You can think of them as an array of Booleans, which I think is a helpful way to think of them. But they do actually physically exist, which means that there is physical sciences lurking around the corner all the time here, and we have to look out for that. So when I am working with a language that I want to deal with these low-level features with, and in this case we're moving towards a cryptography application, so that's why we're looking at this, right? There's basically two things I want. I want the language to let me look at bytes directly. Rust does this. You've seen it. You used it on Wordle and your random number generator. And then I want, in addition to having some way to view them or something, I want some way to work with them as if they are something other than just integers, right? And usually the way this is done is we have a collection of things that are usually called the bitwise operators, and they allow you to use essentially integers to change the individual bit within some byte, right? And you can do this gracefully, and you can do this quickly, and there is hardware support for doing it, and it's consistent across many generations of hardware and across many generations of languages. So we're going to talk a little bit about bytes, or the byte itself, and then we're going to talk a little bit about the bitwise operators. I'm going to explore each in Rust, and I'll provide some Python examples where I can. So bytes are referenced by name within Rust standard in a few places, but there is no formal type byte. Let me show you an example of this. So if I look up Rust byte, and oops, I'm in the wrong screen. So we'll put this over here. Okay, so there's a crate for bytes. There's bytes in standard, and maybe we just look for byte. So bytes does show up here, and I will embiggenify this. The term is referenced, but here it's it's an iterator. It's an iterator. It's a method that returns the iterator. Here's a method that iterates. Right. So we don't have a type necessarily, right? Bytes are just treated as an iterator, the same as anything else. So a Rust iterator is one of its forms of a collection type, right? So I call, we'll use this example, right? Returns an iterator over the bytes of a string slice. Sure, here, right? So if I turn bors into bytes, then I'm going to get a B, an O, an R, and an S gradually over time. Sure, yeah, that's close enough, right? I'm more used to seeing Rust use U8 for these. And this is where we see that from. So let's look at my preferred way of thinking about information in Rust is as U64s, because that's the way my computer is designed, right? So what we're going to do is we're going to ignore the words endian for now. Okay, creates an integer value from its memory representation as a byte array. Okay, this is getting closer to this idea we're talking about. An integer value is the thing that numerical computing works with. Its memory representation is the physical representation in charged and uncharged transistors in the physical device of my computer, right? And as soon as you start doing this, you have to start talking about complexity. This introduces forms of complexity that would otherwise not be exposed to the programmer. And so this is how we're seeing the integer type, U8, placed in an array of length 8. So this is an 8 things of 8 bits, not 8 bytes. That one's the first 8 refers to bits and the second 8 refers to bytes, right? So this is an array of U8s. So we're using U8s to store bytes. Why is that? Well, do we really need a separate byte? We already have something that stores 8 bits of information, right? The difference is linguistic or philosophical, right? So the language doesn't need to furnish a new type for us. So why would it? And to me, this makes enough sense. I would probably just, well, I mean, the nice thing about U8 is that it's short, right? But I would probably just call that a byte, So here's some of the references I showed you. There's lowercase bytes, which is usually methods. There's uppercase bytes, which is usually iterators. I'm calling that a form of data structure. We don't have to think of it as data structure. I just need some word to describe it. There's some Rust language infrastructure around this thing that contains certain types of information. And when we look at things that to me look more like bytes, they often come back as U8 arrays. Oh, I'm missing a paren there. Let me see if I can fix that. Okay. I think that'll take a minute to show up. In any case, collections of U8s. So when we're looking at bytes, bytes are divided into collections of 8 bits. So every time we're looking at a collection of bytes, we're looking at collections of things of 8 bits. Is this still not showing up? My renderer is very slow today. Oh, it's still thinking. There it is. Okay. Here we go. Okay. So you know I love random numbers. They're some of my favorite numbers to look at. And actually, these aren't random numbers; they're random bits. So let's go ahead and just look at some stuff. I think I'm gonna make cargo new. Let's see. Today is 30. Name bits PCS none. Is that right? CD 30. Okay. All right. So here's my package. I think it's crate for today. Let's open source main. And we'll just bring this over. So this is poorly formatted. There's two ways I can deal with this, and I'm going to do one of them on the first two lines and one of them on the second two lines. I can go, I'm in insert mode, so I can go back up, let's see, a couple lines. I can go to the beginning of this line. I'm going to show visual block mode because I don't think I've shown visual block mode in this class, and this is actually why you should use this. I don't even remember if I opened Vim or NeoVim. Historically, you have entered this thing called visual block mode, which is the way to enter edit multiple lines at a time with Control V. I have a confession. I'm currently on a Windows device. I know. I'm sorry. On a Windows device, when you press Control V, the host operating system thinks you're talking about the operating system's paste buffer, right? So we can't use that. So helpfully, most Vim installations now expect by default you can use Control Q to enter visual block mode. I'm going to do Control Q. This says visual block mode at the bottom of my screen. I think I can highlight that. So this is visual block mode. That doesn't look like a visual block to me. Well, I can use the movement keys to go up or down and select multiple lines, okay? So I'm going to select multiple lines. I'm only going to select 2 lines here, but I want to point out you can select blocks in both dimensions, okay? So let's see. I want to go back. Okay, so I've selected these 2 lines, and I could have done this for all 4 lines. And now, from visual block mode, so while I'm still in visual block mode, I'm going to hold down Shift and then press I for insert. This is going to put me into insert mode, but I'm actually in insert block mode. What I'm going to do from here is I'm going to indent this line. I could press Tab, but I'm not quite brave enough to do that, so I'm going to press space a few times. And that aligns my indentation. And now, it looks like I only edited 1 line, and that's true for now. But when I leave the special insert mode, when I press escape, I'm going to leave insert mode and visual block mode and go back to command mode. And what that will do is that will apply the insert I did to a single line to every location in the block. And so it will auto indent standard. So see, my cursor is still on line 3, but I successfully also indented line 4. So I wanted to show that to you. And that is Control Q. We can highlight some things. We can remove them, and we can save and exit. Your other alternative, depending on what formatting you're trying to do, is you can use cargo format. Oh, I can't type. And you see this will auto-format it as well. And then from here we can cargo, nope. We can cargo run. And there's some bits. How many bits are those? Well, if I had to guess, I would say usize bits, because we take the number of bits in a usize, which on my device will be 64. We divide that by 8, and then we take them 8 times. So this is the 8s going back and forth all over the place. Anyways, you don't have to believe me that this is 8. Can I do this? Ooh, yeah. Okay, that didn't work. We tried. I wish I knew all of these commands better. Print len. Oh, and I used the wrong quotes again. Boo. Look how slow it is when you can't use Vim commands. Single quote, close parens, double quote. So this is of length 64. Okay. Now, I think if I cargo run a few times, whatever. I'm not going to get the full 64 every time because I'm only going to get leading 1s. It's not going to print the leading 0s. That's no problem. We can fix that by, I think I specify leading 0, 64 values. And that will give me my leading 0s. And now I will get 64 values every time. See, these are horizontally aligned. And they were not previously. Okay, cool. So that's bits. Go ahead and test this. This is what you'll see, or you'll see something like this. Since I'm a teacher, I feel obligated to point this out. We edit source.main. The code compiled again. We ran the code without changing the source. So no changes to the source were made in between this cargo run and this cargo run. No compilation step. It starts with finished. Starts with finished. And this finished, which is now much faster, right, is just checking to see if the executable is there. And the executable, you can find it under debug bits, right? So I can just run that as the executable. Is that true? Did I make that up? Target, debug, debug, bits. Same thing, right? Cargo run just looks for this automatically, and if it's not there, makes it first. And this thing is the output that would be from rustc. We can even, I'm sure there's no reason to do this, but you can look at the file itself. That's pretty interesting. Wonder what that all was. But anyways, there we go. Oh no. What have I done? Oh, because these are all commands, because they're semicolon separated. So those will all run. Okay, well, and they're all, there we go. Okay. Never use computers. Okay, fun. I want to now introduce the bitwise operators. It's 30 minutes in, it's time to actually do some of today's class. And so I'm going to do this with just some minor changes to source. So how am I going to change this? Well, I don't need 8 bytes to do this. I only need 2 bytes because I'm going to use mostly binary operators. So I'm still going to need U8. Oh, by the way, this 0 right here, that just represents the initial value. So I'm initializing this to some value. I don't know why I'm doing that. I found something that did that once, and it worked. You know, I'm going to get rid of it and see if this code still works. Okay. Now I know what you're thinking. You're thinking, oh no, I bet you have to change this line. No, so read exact is going to look at how big this buffer is, and then read exactly that much information. Isn't that great? That's just so nice. Okay, so we don't have to think about this at all. And then these next lines are now fake. So what are we going to do instead? Well, I'm going to take x. X is going to be a U8. And it's going to be the buffer. This code's wrong, right? That won't work because x and y aren't defined. This has to be buffer. What am I doing? That's crazy. Okay. So we're going to take buffer 0. It doesn't actually matter what order we do this in. And that's going to be buffer 1. And then we can print these out. I'm going to say x equals x as a 0 prefixed 8-digit binary value. And I'm going to say y equals, because you're probably wondering how I know this. I think this is just the same as Python. I don't know, but I think the format strings in all the modern languages are the same. So I never looked up how to do this in Rust. It just worked the way one of the other languages I know did, and then I stopped thinking about it. Oh, that's not a value. Oh, you do have to put the 0 there. Oh, wait, maybe I don't. I just lost my semicolon at the end of the line. Okay, let's see if this is allowed. Yeah, okay, so you do have to initialize this to some value. So I'm going to initialize it to 0. Cargo, run. Cool, so here's some, you just see a bunch of random bytes. And I know what you're thinking. You're thinking, wow, isn't it so annoying to see all of this trash every single time I run my code? Yeah, it is. No problem, I got you, right? Okay, so that's how we see a byte. And now that we can see bytes, we can learn about bitwise operators. So let's go ahead and do that. There exists an operator reference. It's right here. I completely made that up. That's the wrong tab. Okay, here we go. This is in the Rust programming language, Rust book. It's over here in an appendix. So this is 22. There's a lot of chapters. And anyways, here's all the operators. What I do with this, well, I actually just found the source for this on GitHub. It's in source. I went to appendix to operators. I found this table. I looked at it raw, and then I just stole this markdown table. And I put it directly on this slide. You don't have to believe me. Let's see. It's right here. So anyways, that's how I make these slides. I thought that might be fun for you to see. Okay, so here is the things. Ooh, I think I just hit my mic with my hand. That might have sounded terrible. I'm sorry. Oh, I apologize. Okay, but back to work. These are the things that I consider bitwise operators. You'll notice they do not all have bitwise in the name. These ones don't have bitwise in the name. They're kind of weird and squirrely. These ones are also in your favorite programming, or no, here, I'll clear this. These are also in your favorite programming language, Python. I bet you really like that number, right? I just typed I to enter insert mode in the command line, okay. So these are like a little bit different. I do think of them as bitwise operators. Maybe that's actually uncommon. But I call that a bit shift. I don't just call it a shift. So to me, the name of that does have bitwise in it. And then these other ones are quasi-logical operators, right? So this is not logical negation, but they call it bitwise complement or negation, right? We have bitwise and, we have bitwise exclusive or, XOR, and then we have bitwise or. Oh, well, those are just logical operators. We know what these are, so these should be easy to understand, right? So how are we going to understand these? So here's the conceptual model I'm going to articulate to you. You don't have to think of it this way. This is the way I have come to describe it, which I think makes sense. We're going to imagine a byte as an ordered collection of bits. It's of length 8, that is irrelevant, but you can think of it as a list, an array, and now if you know Rust vectors, you can think of it as a vector, but it can be a Python list, it can be a NumPy array. No problem, it can be a Rust vector. We imagine the bit as a Boolean. Why? Well, really, it's 0, 1, right? But I think of the Booleans as 0, 1. I don't think of them as true, false, right? These are the same words, right? You don't believe me. That's okay. Let's see. For I in range, I don't know. This is false, right? But there's, okay, no, that is true. Okay, and then, so we can say, I bet this doesn't work without parens. Yeah, because of precedence. But if we throw parens in here, oops. This is not true in Rust, because in Rust, 0 and false are different types. In Python, there's no types, not really. There's things that look like types or pretend to be types, but there's representation, right? So apparently, these things are equal to each other. And what this actually means is we can take this and we can recursively substitute it, which is kind of cool. So I think that's fun. Okay, let's get out of Python before I type any more Python, right? Okay, so we're gonna do some Python. Okay, Python, you can't get away from it. Okay, so let's get some Python. I sure hope I have NumPy on this device. No, I'm not getting all of NumPy. From NumPy import uint8, which is U8. We just put the int in the name because historically that was done more commonly. We're going to introduce things as bytes. We're going to create an x and y, which are going to equal the byte OXOF and the byte OX33. What am I doing here? This is 4 zeros, 4 ones. That's 2 zeros, 2 ones, 2 zeros, 2 ones. Just to have something to look at, okay? This formatting is unnice, right? Why is that? Well, if I put these on separate lines, they don't line up well. So you get to use this like ludicrously annoying format code here, and this will line them up. Is that a Python new line? Yeah, so now things are lined up nicely, right? And so this will be a little more useful when we get on to the next thing, which is let's take a look at X. I think that's XOR. we will put in a new line here, and we will say x, y. I'll just get rid of the equal. So I think this will align horizontally. So I have 1, 2, 3, 4 characters. That is 1, 2, 3, 4 characters. Okay. And so we can see how this symbol, which is must be XOR, right, is applied to the byte arrays. Okay. And let's think about how this works. Okay. So here's the example. Is this literally the exact same thing? Oh, no, I just didn't put it on one line, right? Ooh, I kind of like just using this sign better. That's a little bit nice. Okay, but what are we looking at here? Well, I have these x values, 4 zeros, 4 ones, 2 zeros, 2 ones. So what's going on? These 4 ones in the middle are set. Why is that? What do they have in common? Well, for these 4 ones, the corresponding byte in the same, the corresponding bit in the same position of the byte, okay, is set in 1, but not both of the arguments. Okay, so if both of them are set to 1, we get a 0. Why is that? Well, because this is false. Okay, and if one of them is set, then we get a 1, which is true. And if both of them are not set, then I get false back. So what's really going on here is we're just taking XOR, and there's no real XOR in Python, right? So we're gonna make this a little bit easier in a minute. There's no real XOR in Python, but this is taking exclusive OR and applying it to each individual byte. And the reason there's not XOR in Python is because you can use this, and it gives the same. So because it's the same thing as inequality, it's kind of weird how it's an argument. We can do the same thing with AND. And I think we'll understand a little bit better. It's only when all of the bytes are set. We can do the same thing with OR. I'm assuming that's OR in Python. That might not be true. I might be telling lies. I'm not. Go as OR. You can step through this in a variety of ways, but let's look at 2 quick examples, right? One way to think of this is that we can transmit these bytes into something else. And one of the other things we can transmit them into is an array of Booleans, right? So let's write toBool. And I'm going to do this by taking, I'm going to write a lambda expression, and it's going to take a byte, and it's going to take that byte, and it's going to loop over that byte, and seeing if there is a 1 at each location, and then outputting true if there is, right? Okay, no problem. We can do that. So how are we going to do this? So we're going to take lambda of x, or y, and we're going to do list comprehension. We're going to do that list comprehension for I in range 8. Why 8? Because there's 8 bits in a byte. And then for each one of those bytes, or each one of those bits in the byte, I wish the names weren't so similar. It really gets me. Well, I'm going to see if there is a 1 there. So how I'm going to do this? Well, we'll start with, you can debug this a little bit, but so I'm going to say, hey, I know that I need to check to see if the sort of, I don't know, nth bit is set equal to 1. Well, I know what the nth bit represents. It represents the nth power of 2. So I can take the nth power of 2, I can divide by that, right? And that will give me how many of multiples of that power of 2 I have. So I'll take I, and I will raise 2 to the power I, okay? And so that's the power of 2 I'm looking at. I want to see if one of those powers of 2 is an x. But I need specifically for there to be an odd number of that power of 2, right? So if we consider 17, for example, if I divide 17 by 8, there are multiples of 8 in 17, right? there's 2 8s and a 1, basically. But those 2 8s can better be represented by a 16. So if I'm representing 17 in binary, I will say there is 1 16, no 8s, no 4s, no 2s, and a 1. It will be 1, 0, 0, 0, 1. So in order to detect that 1, what I have to do is I have to make sure there is an odd number of multiples of this value. So I'm going to check to see if this value is odd by taking its remainder when divided by 2. So that's the 2 there. Okay? And I think that's it. Let's go ahead and look at this. You'll see I have additional lineage here. That's to turn this into a Boolean. To bool. And we will take x. Right? Okay. So what's going on here? This is real hard to read. No problem. I can fix that. Bool I. For I in to bool x. And this gives me true, 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 false, false, false. True, true, false, false. True, true, false, false. Right. That's kind of cool. I think that's kind of cool. Once we do this, I guess those things aren't Boolean, so let's fix to bool. 2 ways to do this. You can just put bool here. Or you can use this 1 equals. Both of those turn into a bool. Once you've done this, it's not that bad to sort of just map over the kind of different values we have here. Did I skip I skipped something. Python lacks an OR expression. Oh, I just do it manually. Okay, let's take a look at this. So, if we take all of true, false, and then we take, this is somewhat annoying because it's split up. Do you see that? The column heading for this is like up here. What is 4 left? It completely split. So anyways, this is what we're supposed to get, which is a markdown table. You can express this in markdown, which is that, hey, this is the same truth values as XOR, right? So, excuse me. What can we do? Well, for x and y, if I take x or y, and let's turn that into binary, this thing will be the same if I to bool that. So that's false, false, true, 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 false, false. That is the same as if I convert both of them to bools. To bool x and to bool y. If I zip these up, and I say x or y for xy in, I should say AB. A, B. This is the same thing. Mapping XOR, such as in a for each, over the array of Booleans is the same thing as applying the bitwise operator and then converting things to a list of Booleans. That's what I'm trying to express to you here. Do I think that's clear? No, I just think it's awesome. Okay, so take a look at this. What's going on here? Okay, so you can go into operator and import and or an XOR. This is what it looks like. It's a built-in function, and you can apply it to values. You can't use and is taken, right? So it has an underscore at the end. Operator has all kinds of things in this, I think, from operator, import, add. Cool. So sometimes you want to have the operators, so you can use op here like this. Perhaps it's more clear here. So I am going to loop over the operators. I'm going to apply the value to each, and I'm going to take a look at this and say, oh, hey, that's and, right? That's or, these two here, and then these two there. So that's or, and then we already looked at XOR, right? So we can look at this for everything, right? You can also grab not from operator, I think. Might be an underscore not. This will be like 17 or something. I don't know, not particularly useful. Maybe they call it complement or something. Anyways, bitwise negation in Python, not my favorite thing, but we can look at bin x and bin negation of x. Now let's put them on their own lines. Oh, they're still not lined up, but I don't want to use print format codes. So you see these 4 bits correspond to these 4 bits, and then there's 4 implied zeros here, and those are these 4 zeros. So that's just flipping every single bit, not too complicated. This is bitwise complement. This is not, tilde is not used in Rust, so just don't think about this, but I wanted to show it to you. The Rust operators are otherwise the same. Okay, so let's look at and vim source main. Okay, so I'm keeping dev random, I'm keeping buffer, I'm still reading exact, I'm still unloading the buffer into 2 variables. There's probably some way to do this gracefully with loops. I used Python for years before I learned about operators. But what's going on here? I'm going to show you this operator, this operator, this operator, and that operator. So let's just take all of those real quick. I don't know why I'm using the mouse. Okay. So what's going on here? Exactly what we would expect. The difference is I'm grabbing random values, right? But what's this? So this is logical OR. How can I tell? Bunch of ones. I think the expected number of ones with a logical OR operation is 6. The expected number of ones with a XOR operation is 4. And the expected number of ones with an AND operation is 2 or less. It's either 2 or 1. It's hard to think about the probabilities, right? But this all makes sense, right? So there's many ones here. Oh, the expectation's higher because there's 5 ones in this value. So what do we have going on? There's only a 0 in both branches here. These differ in, let's see, like a lot of positions, right? So they differ in position 1, position 2. They do not differ in position 3 because there's a 1 in both places. And then again, they don't differ in position, whatever this is, 7 or however you want to call it, right? It's the 6th index position from the lowest bit, right? So those are both a 0, right? The AND, it's quite similar. These things don't line up that well, but they both have a 1 right here. And that is that's the 4's digit, because that's 1, 2, 4. So the 4's digit is set. Bitwise negation is as expected. You take all the 1s, turn them into 0s. You take all the 0s, turn them into 1s. No problem. Easy. Run it again. Take all the 1s, turn them into 0s. Take all the 1s, 3 in a row here, turn them into 0s. That's fun, right? Many 1s. Okay, that's the Rust operators. Go ahead and take a look at this. And from there, it's time to talk about endianness. Okay, so I'm actually going to take a pause here, and then I will synthesize the video together later. And it is time for endianness. All right. Okay, so endianness refers to a problem we have to deal with. Okay. What is this problem we have to deal with? Well, I just spent 52 minutes yelling nonstop about how cool bits and bytes are, right? But the first 10 minutes of that was spent discussing in great detail that these things are not the integers. They don't represent the integers. They don't even represent a finite subset of the integers. We'll talk about some of the implications of these numbers being finite later. There's that you can like divide 0 by 2, right? Like that's weird, right? But so say you're one of the early architects of computing systems, and someone says, "Hey, that's a great computer you got there. Can you divide 6 by 7?" And you're like, "Well, no, because that's either 0 or 6/7. Or perhaps it's 1." And we're like, okay, well, what can you do? Can I type my favorite number, 123, into that device? And you say, well, no, actually, you can't do that either, because you have to tell me if 123 is in base 10, base 4, base 8, base 16, base 64, whatever, right? And so then finally, the thinking goes, Well, why don't we just tell the computers about base 10? We'll just go into the hardware and we'll say, look, I've got a 3-digit number, 123. I want a transistor that says if there's a 0, a 1, a 2, or 3, or so on in each one of those digits. And nominally, some of the earlier computers worked this way. I don't know, I never checked, but there's an apocryphal tale that the early computers were written to recognize base 10 until some mathematicians looked at them and were like, are you out of your minds, right? Like there's absolutely no reason to do that. So this is perhaps one natural way that we would think of, because we have 10 fingers, you know, because we went to elementary school and we were taught to count to 10 to store information in a computer. And so here's a way to say, okay, I have a 3-digit number. I need 30 transistors to store the values. I could design this. These circuits exist. They can be made, right? I could go to, I guess Radio Shack probably doesn't exist anymore, so wherever you buy transistors, I could go buy 30 transistors. I could solder them to a board. I could have a physical circuit board, and then I could attach them to some switches, right, and put current through them. Well, how much information are those 30 transistors actually holding? Well, the answer is they're storing 10 transistors worth of information. They're storing 10 bits. When we look at the atomic unit of digital information, the bit, we only need 10 of them to store the same amount of information that is needed to capture 3 decimal digits that require 30 transistors, 3 each per digit, to store. Why is that? Well, because the log base 2 of 999 is less than 10. You don't believe me, that's fine. Print, can I do this? X equals 199. Print x dot bit length. I bet that'll work. Right. To get over 10, we have to go up to 1025. We're allowed to fit 1024 in there. Oh, no, it's probably 1023, right? And then 24 rolls over because we have to have room to store 0, right? You only need 10. Okay. Point is, decimal encoding, if we did it in electronics, we would be wasting a ton of space. 2/3 in the 3-digit case. And you can extrapolate this in any directions you want, right? Any fans of a million in here? Same ratio, right? Because this would be 60, right? 10, 20, 30, 40, 50, 60, 20 bits, okay? And we can store this in binary by only storing multiples of powers of 2. Very easy, very comfortable. How do we do this? I believe this is CS1 review, so I won't spend over long on this. But, well, I take a number, and I do sort of the same process I did to convert a byte into an array, you know, which is I was like, hey, is there a byte at this position? Because I was able to use the numerical operations to turn bytes into arrays of booleans. Well, we can go the other way. We can take a numerical value and turn it into an array of booleans, right? And that array of booleans can correspond to an arrangement of switches in electronics, right? So we just say, hey, I've got a 2, I've got a 16, I've got a 32, and I've got a 256. So what is this? This is 256 plus 32, which is 288, plus 16, which is 304, plus 2, which is 306. Am I right? 0, 1, 0, 0, 1, 1, 0, 0, 1. Wait a minute. Hold on. This is backwards? Oh, it's backwards. Oh, and I probably want to end it. That's the same. 0, 1, 0, 0, 1, 1, 0. Did I miss one? Do I have to stop at 1? There it is. There's the 1. Oh, that's this one, because, yeah, whatever. You stop at the index. Okay, right. So, hold on. When I asked for 306 in binary, I got this number. But when I started from 0 and then went up to 9 over here, I got it in a different order. That's dumb. We have to make a decision. Why is the ones digit n to the power 0 leftmost? Oh, this is 276. I didn't update my slides from when I used this in 276 to 271. I'm going to see if I can change that without exploding everything, because I think I can. Can I? I have to find it. So I'm going to put a 1 there. I don't know how long this will take to render. Okay, I think this is going to work. So, why is the ones digit n to the power 0, which is 2 to the power 0 or 10 to the power 0, leftmost? We call this the least significant digit, or LSB. This is written lowercase LSB. I most often see that as all capital LSB. I'm going to say in the natural language, English, which I'm speaking, we commonly place the least significant bit, no, digit, yes, the least significant digit last. So if you were taking CS276, game development this term, the 6 would be last. If you're taking CS271, this class this term, the 1 would be last. But if we start from 10 to the 0 and then go 10 to the 1, we'll do the 1 first. This is weird. Here's how I justify this. In spoken word, we often lead with the biggest value, or the most significant digit. And I say that's because 200 of something is closer than 299 of something than 0 of something is to 9 of something. We care less about this digit when we're dealing with hundreds of things. There are around 300 million people living in the United States. There are around 700,000 people living in Portland. I'm only giving you one digit of precision there, right? 3, 7, and then I'm giving you some order of magnitude, right? I'm not telling you whether an odd or an even number of people live in Portland. I don't know that you could determine that. I don't think you could determine, I don't even know if you could determine if an odd or even number of students attend Willamette University, right? You're going to have to start making really strong conclusions about things like part-time status, right? You can maybe get down to the level of a class, but, you know, a student comes through part of add drop. Is that a fractional student or not? If those fractions add up to 1, these questions get really hard to answer, right? But it's pretty easy to say there's about 30 students in a class, right? One digit of precision, very easy. So I think that's why we do that in natural language. In programming, we often lead with the lowest numerical index, right? That's because array 0 becomes before array n. And if you're dealing with zeros first, there's an inclination to say, well, shouldn't I deal with the 0 with power of something first? Shouldn't I say, well, I have some number here. It's odd. It's a multiple, or it has 1, 2 in it. Doesn't have any 4s. It has an 8. Has a 16. It doesn't have a 32 or a 64, and it has a 128, right? Maybe that's a reasonable way to think of things. Lots of reasons to do things that way. When you're adding numbers together, right? That's the direction you carry. Can I just mark on this? Tools. You know, if I do multi-digit addition with carries, I start at the ones place and go to the tens place, then the hundreds place, and so on, right? So I claim this is confusing. Oh man, there's that 6 again. Don't worry, I'm changing it. It'll be fixed eventually. And when I wrote this naively, I also had to reverse the direction of my tool num, right? So it is odd that depending on whether you're dealing with numbers or strings that represent numbers, you kind of get a different sense of what comes first, right? And that's weird. That says equals 6. That's great. Oh, it's not actually an equation. Okay. So this is weird. This is weird, and this should annoy us. Let's walk through an example. I think here's a really realistic, reasonable example. Say you love Instagram, right? Say you have this many followers on Instagram, which is apparently this many in decimal. Meta did something that annoyed me today. I think Zuckerberg said that Mark Zuckerberg, the owner of Meta, people will be significantly cognitively disadvantaged if they're not wearing meta goggles by 2030. I think Mark Zuckerberg has been wrong about everything he's ever done his entire life. But that's okay. You don't have to follow me on Instagram. But let's imagine we've got this number, which is a large number in the sense that it is bigger than 1 byte. So the value of large is bigger than 1 byte. So we're going to imagine it's 1969. I only have 8-bit integers. And so each one of these 2 digits has to be a hexadecimal representation. So let's step through this example. Well, let's go ahead and start writing some Rust. What do you say? We all like Rust here. We're Rust programmers. Rust is fun. What do we want to write? Well, let's go ahead and read in the text someone is going to type to us that is their number of Instagram followers expressed in hexadecimal, which I'm sure is how we track all of these things. So I'm going to need to have a new string, the string data structure, the data structure that can contain a string of arbitrary length, which requires some infrastructure, requires some things around it. They probably have to store their own length, something like that. And I'm going to take that, and then I'm going to go into the standard library. I'm going to go into the IO functions of the standard library, and I'm going to get the standard input function. This is going to correspond to, specifically, the function that when called will return a value. And what is that value? That value represents how Rust can look for things that I type into the command line while the Rust program is running. I'm going to ask to read a line from that, and I'm going to need to place that line I read somewhere. Where am I going to place it? I'm going to place it within the variable that I created in the previous line, guess. There's a little problem. In order to edit that variable, I specifically have to allow Rust to mutate it. And separately, if I ever want to look at what is in guess again, I cannot grant readline ownership of guess. If readline consumes guess, then I can never look at it again. So I'm only going to let readline borrow guess. I'm going to give readline a mutable. They're called references, and I'm going to say, guess, you are allowed to change the readline. You are allowed to change the values in guess, but you have to let me get to keep seeing guess. That's what that means. If something about Rust is found confusing, apparently it is that. I think that's just because there's no. I think it's just because it's new. I don't think it's inherently confusing. So you're learning that right now. Let's just print out guess. I'm going to use the debug macro. I think this is allowed. Maybe it's not. I don't know. So let's go ahead and run that. Hello. There it is. Guess equals hello. There's a new line there. That's kind of sketchy. Let's try some things. What happens if this isn't a reference? Oh, then that doesn't actually make sense. I have to I can only specify mutability on references. What if I just get rid of the mutability? Which I think I do like that. Is in this run? No, not allowed. Why is that? Because readline specifically wants a mutable reference to a big S string. Why is that? Basically, for the natural language reason I described to you, I have to let readline put something in a string, but I also have to be able to read the string when I'm done with it. Okay, so we put the mutable reference in here. I keep getting on the wrong side. Oh, I need to press A instead of I when I do that. What happens if this thing isn't mutable? Oh, you cannot borrow guess as mutable. So I cannot let readline mutate guess if I don't let anyone mutate guess. So I have to set guess to be mutable. What happens if guess is equal to some string? That's the wrong type. This is called a string slice, I guess. But this is a string literal. I need a big S string. Readline needs the data structure, right? So it needs access to a data structure, it can update it, cannot just look at some other string. So, what do we do? I think this was string new. There we go. And then this works. Hello. Okay, so that's how we read things from a line, okay? I'm using the debug formatting of print here. That's more lines. See, this is shorter. That's why I'm typing that in class. Let's run some nonsense. We'll say nonsense instead. Shout out the nuns. Okay. All right, so to read in hexadecimal values, what are we going to do? We're going to read in the string. Okay, we can do that already. No problem. We're going to break it into chunks. Okay, that's going to be a little exciting. And then we're going to convert the 2 character chunks to numeric values. Easy, we can do that. We're smart. So what are we going to do first? Well, first thing we're going to do is let's go ahead and read in the values and print them in pairs, okay? So how am I going to do that? Well, I got guess here. So let's see. For C, for the character, in guess, and we're going to look up the characters. I'm not looking at the left-hand side of my screen, but I can tell it's there, so it can help me if I get stuck. We're just going to initially print line. Let's just print C. We'll do a counting variable. We'll set it equal to 0. And then if count %2 is equal to 1, we'll print line, and then otherwise we'll print no new line. Are there easier ways to do this? Yes, of course. And then we're going to increment count. Is this going to work? What do I do over here? Oh, that's banned. Value borrowed here after move. Okay, so I'm just not allowed to debug it. I think debug consumed guess, so then no one else was allowed to look at it. I solved that by removing the debug statement. There we go. OX 1, 2, 3, 4. What do? Count up my characters. If I'm an odd number of characters, I dump a new line. If I'm on an even number, I just print without a new line. Easy. Easy. Maybe not easy. I don't know. This is for loop. Do we like for loops? I don't know. You can like for loops if you want. For loops are okay. Here's a problem. That 5 shouldn't be on its own line. Because 4, 5. Because this is a byte. That's a byte. And that's a byte. So that's terrible. Here's another problem. That's not a number. So we need to get rid of this. And then we need to shift all of these down if we're on an odd numbered string. Okay? No problem. So we need to make sure we begin rather than end on a possible singleton. So I'm going to skip the first 2. I'm going to run to the end of the string. And I'm going to build doubles back up. Easy. How am I going to do this? Well, let's start by skipping. I'm going to create a mutable reference to the characters, which is going to be guess.chars. Okay? I'm going to map over C and C's. But what else am I going to do? Oop, that needs a semicolon. I'm just going to take next twice. This is going to take off the first 2 elements of my list, okay? I have no idea what that's going to do. Let's try that again. OX 1, 2, 3, 4. Okay, cool. It's getting rid of this. Now, what happens if I put that in? We get a problem. We don't get anything, okay? That's okay. OX 1, 2, 3, 4. OX 1, 2, 3. Still splitting the 3 out. So, what are we going to do? We're going to solve that with a different problem. Looks like over here I did this with a Boolean instead of a counter. That doesn't matter. That's totally made up. So what are we going to do? I'm going to traverse to the last character. How am I going to get to the last character? Well, it is time to introduce recursion. And so we're going to write the non-recursive way to get to the last character first, and then we're going to build this up to recursion. So we're going to get the last character. What is it going to be? Well, last character is going to take C's. What is C's? This is the type of C's. It's a standard library string characters. I wish I were making that up. That's the type I have to specify. C's, standard, stir, chars. It's going to return a character. We're going to keep track of a candidate. So we're going to create a mutable value. This is the final. I was going to call it last, but I already have final. It was finals highlighted. End. Fin. Okay. It's going to equal C's.next. So I'm going to grab a character. I'm going to say, I wonder if this thing's last. And then I'm going to say for C and C's, final, fin equals C. Then I'm going to return final. Nope, I'm going to return fin. Man, Vim doesn't like that. I wonder what's wrong with that. Okay. Last C's. Cargo run. Expected type. Oh, yeah, it's a char. Apparently that's the character type in Rust. I know that. No one told me anything. Remove this mute. I don't need that anymore. What's going on here? Oh. And let's look at the head of source main. What's going on here? So this thing is C's.next. That might not exist. I don't know how long this thing is. There might be nothing in it. It's a bit of a problem. Which means that I need to unwrap this thing, because this could either be some C or none. Now, I'm just going to generously expect that someone's not going to give me a hexadecimal string of length 0. And then what else do I need to do? Well, I'm updating C's because I'm popping things out of it. So that needs to be immutable. What's going on here? There's a new line at the end of that thing. Remember that? You remember when we did the debug and there was a new line there? So what we actually need is, like, I don't think I'm going to stick with this. While C is not equal to some new line, I don't know, C equal C dot next dot unwrap. I don't know. This is getting a little silly. Yeah, it's C's dot next. Okay. I use the S at the end when it's a collection of the things that are, so C is an element of C's. That's how I think of it. That's my name scheme. We have to use a let binding. Oh, we just want fin. I don't know what I typed. Fin. Change these all to C, actually. I'm committed now, but do a replace. %s fin C. I didn't save it. Okay, %s fin C. Enter. Oh my gosh, my hands are doing things that my brain is not doing. Okay, let's save and exit. There we go. Cargo run. What's going on? Expected character. Found option character. Why is that? Well, okay. This is a sum. I unwrapped the sum. Okay, so gotta do this. Cargo run. And at this point, it occurs to me that I should just do cargo run when I come out. Okay, so OX 1, 2, 3, 4. Still the new line. Okay, great. So what we actually need to do is check next. And at this point, it's time to just write recursion. Okay, so I'm going to use some pattern matching here. What I'm actually going to do is, instead of writing a for loop inside of this thing, which is super annoying, I'm going to pattern match. And what I'm going to do is I'm going to return a character option. So let's come over here. Let's go to the first line. Let's go to the end of the first line. We just need to return an option here. This is why options exist. This is why we want them. Okay, and we're just going to get rid of all this stuff. All this stuff is bad, except the return statement. What am I going to return? Well, what I'm going to return is actually dependent on the result of another expression. So what I'm going to do is I'm going to match. What am I going to match? I'm going to match what the next value in C's is. So I'm going to match the character I'm looking at. So previously I calculated C's next. And I'm going to look at C's next, and I'm going to decide what I'm going to return based on that. Okay, so C's next could be a variety of things. It can be some value, or it can be none. If there's no C's next value, well, then I just need to return none because I don't have any characters, right? I'm going to put a comma here, and I'm going to close my brackets. I have just noticed that there is a question mark here because I wasn't holding, or no, I just typed the wrong character. So I'm going to fix that. I'm going to go to the beginning of the file. I'm going to go to the end of the line. I'm going to replace do it less than. Okay, let's go down a few lines. Okay, if there's some character here, well, what's that mean? Well, there could actually be a couple different possibilities here. But if I have been returned some last character, that's probably the last character of everything. So I'm just not going to look at C's next. And actually, what's going on here? I'm matching on last C's. So this is just returning exactly what I get, right? What I actually need to do is I need to decide whether to return the current character based on what the last character is. So I'm going to include an internal match statement. So if there is a character left, so if C's next returns something, I'm going to return the last of the remainder of C's if it's not none. So I'm going to match the last of the remainder of C's. So this is the current character. If the current character exists, I'm going to look at the rest of the characters. I'm going to look at the rest of the characters, and if there's no characters left, if there's some characters left, I'm going to return that character. So I just did M because it's next after N. Maybe this is easier to do C and D, because D is after C. If there is already some discovered last character, I'm going to return that. And if there's not, I'm going to return this. Because if the next thing is none, that means I am the last character. Sum C. Okay. Where's the loop in here? The loop is right here. Last calls itself. How many times does it call itself? Last calls itself until C's is none. So this will run exactly as many times as last. And you don't have to believe me. We can debug C's every time. And I might have to pass this as a borrow. So I have C's. I have 1, 2, 3, 4, 2, 3, 4, 3, 4, 4, new line. And then I am now going to return it. We look at this, last C's is going to return the sum new line. Okay, so what we actually want to do then is, if we see a new line, we want to return sum C. So we don't want to return this value in all cases. So sum D is what is matching with last CS. So if the last of C's is sum new line, we want to return sum C. Oop, that shouldn't be it. And there we finally get the 4. It's still packed up. That's okay, right? So we're getting the 4 back here. And perhaps you want to unwrap this or something. I don't know. You can't really unwrap it because it might be the case that, I'll show the example. That's not great, you know. Really need to check for new line here, because the new line can be the first character. There we go. We get a none if there's nothing there, right? And so what's going on here? Anytime we see a new line, we either return the last character if there is one, or we return none if there isn't anything, right? I hope that makes sense. If this doesn't make sense, try and write in Python. You can't write match statements in Python, but you can't write if-else matches. This is really cool. What I want to point out, what we've done here, this entire function is written inside a return statement. This is a one-liner, right? We've split it up into other lines. What are we going to do from here? Well, yeah, we tried it out. We're having fun. We're having a great time. We need to make pairs. So how are we going to make pairs? Well, I just have fantastic news for you. This is not that bad. What's going on? There's a typo on this slide, I think, because that bracket doesn't close. We'll get it to work. Okay, so all we have to do now is print things out in pairs. How are we going to do that? Well, if we have some character, C, and we also got past some character, D, that is the last character, instead of returning that D, we're going to get rid of this, and we're going to print, and we're going to print in order C and then D. And then we're going to close the parentheses. Okay, what's going to happen here? Well, we are, from the perspective of some character in the list, right? We are looking at a character, and we know there is some last character. So we're going to print our current character and our last character. And then what are we going to do? Well, we've printed those characters, so now they've been printed, so we now no longer have to consider them part of C's. So the other thing we can return is none. Now, in order to make this expression all fit on one line, because print line is not the thing we're trying to return, we're going to semicolon delineate this, and we're going to put this into an expression block. So this expression block is going to say what is happening here. If I see a new line, the last character is the current character. So I am the last character before the new line. This is the last character to return. If I see some other character, that means I'm being returned some character that is the last character. I'm going to print that character, and then I'm going to say there's no characters left, because those characters have been printed. And if I see no characters, we just have to deal with the no character cases. We should not commonly see these because we're always stopping at the new line, so these branches are kind of not real. I don't think it matters what we put here. We could argue, you know, this should be how are we here? You know, that's bad. We wouldn't expect to be there. But let's check. We're here many times. The reason we're there many times is because when last sees passes a none, what are we supposed to do? Well, we're not printing anything here, right? Did I make that up? When we see that none, that means we got returned none from either here or here. So C and D are not printing out, right? Let's get rid of the, that's not what I meant to do. Let's get rid of the debug statement and just see what we're printing naively, right? We're not printing anything at all. We're returning none. So somehow we are never hitting this branch. And that's not good. So we need to return something else. How are we going to do that? Oh, that's not what I meant to do. So when we see some D, which is anything other than new line, that means we previously returned some C. And that means we're not matching last with none. If we see none from last, that means we are the last character. So we're going to return some C. There we go. Could not compile bits due to one. Oh! In line 10, I'm in a match block. I'm not in a standard code block, so my lines are not semicolon terminated. They're comma terminated. Why is there a none matches with C here? Because none is returned from this thing, which means we previously printed a pair, which means that the current character is the new last character that hasn't been printed. So this is no longer last. This is now last not printed plus print pairs or something, right? And we print the pairs last to first. Okay? Only one problem. We don't print this one. So we have an off by one error in our recursion. And that's fine. Usually the way you deal with an off by one error in your recursion is you write a wrapper function around the recursive function. So we have a little bit of a problem here. The easy way to deal with this is to put an if-let in main, and I'm going to introduce if-let right now. if let sum n equal last sees println n. What's this n? This n is that n inside the sum, so this is an unpack. And so this is kind of a match case. But what this does is it just conditionally does something if a pattern matches. Well, I just looked at the time, and I think I'm out of time for today, which is good because there's only 18 slides left. And I'll just do that Wednesday, and then we'll do the lab. So I think we got this working. I showed you a recursive match statement that's like non-trivial. This is like extremely non-trivial. Think how easy it would be to just do this, like printing out all the characters in order, right? Like that's silly. This is great. We're using option types. We're using match. This is unbelievably cool. I managed to sneak an if let in here. And we're learning about information. So I hope you had fun with this. If you didn't, keep that to yourself.